Algorithms are methods of calculation. In this sense, algorithms are not unique to computers. Humans have used algorithms since they use arithmetic. For example, when adding one number to another, historically, humans have used columns to calculate the answers. Consider the example 254 plus 2448. How do we work it out? We can't just add from left to right, just like we read them. When performing addition, we start from the farthest right number, also known as unit digits, and add two corresponding digits together to get an answer. In our example, we add 4 to 8. 4 plus 8 equals 12. Here, 12 is a two-digit number, with 2 on its farthest right. As the unit digit, we write 2 directly in the previous column, but 1 which represents the tens digit cannot be written directly. In this case, we carry 1 to the next digit and mark it. So we carry the 1 onto the digit to the left and calculate another 2 digits on the left, 5 and 4, which is 9. But we don't write 9 directly, as we have to add the previous 1 to 8. Here, 5 plus 4 plus 1 equals 10, and 10 is another two-digit number. The unit digit 0 can be directly written in the vertical column, but the 1 in its tens place is carried over once again and added to the digit on the left. The rest can be deduced by analogy. We calculate from the right, digit by digit. In this way, we get a result of 354 plus 2448, which is 2802. If we summarize the column addition method, we can find some interesting details. First, there is an input. In our example, this is 354 and 2448. There is also an output, which is 2802, or the calculation result. There must also be a result, as the calculation will terminate. Regardless of the many steps for calculation, imagine we have two large numbers. Both numbers contain 15 digits each. Such digit-to-digit addition will require 15 different calculations. No matter how large the numbers, nor how many additions there are, we will get a result. This is the first thing we found. Second, it's naturally difficult to determine the sum of 354 and 2448 at a glance. That's difficult. People have a natural gift for mental arithmetic, can get the result with no effort. But for most of us, we need to calculate through steps to work out the answer. Showing our answers step by step, only one calculation can be done at a time. One more interesting point: the addition of any two numbers, regardless of the number of digits, the process is the same. That is, adding two corresponding digits and see if there is a number on their right to carry over. According to the previous addition, this sequence of adding, that is one by one from right to left, is the most practical. You can't skip the digits, as this will change the calculation and lead to a wrong result. If we add from left to right, more complex steps are needed, and once a result is obtained, in the next step, we need to adjust the calculation on the left, and this adjustment may be applied to the number on the far left. To recap, column addition from right to left is the best method for simple addition. and the calculation sequence matters a lot to the result. Third, this kind of calculation requires us to temporarily record the carried over numbers. So when adding up single digits, even only a number like 1 is carried over, it needs to be recorded. Sometimes we have no number to carry. The situations will vary. Carried over numbers need recording, and this record is temporary, which won't appear in the final result. It is not an input or a result, but in the middle of the addition, the temporary records are required. Without records, we are likely to make mistakes during the addition, which would render our calculation incorrect. Therefore, records matter during the process. That's the third point. Fourth, we found that for large natural numbers with 3 or 4 or even 10 or 15 digits, the process for each digit is the same. But because the calculations are different values are used to get different intermediate results until the final result is generated. This is the iterative computing and is common in algorithms. Iteration refers to the repeating the same step with different values to calculate. That's the fourth point. Fifth, except for the farthest digit on the right, we should pay attention to whether there is a carried over number from the right. This will make things different and require different calculations, because multiple cases exist in the process, and calculations vary with actual situations. This is the branch computing method common in algorithms. That wraps up the 5 interesting points we found during the column addition. Put simply, after several calculations, one set of inputs turns into outputs. This is what an algorithm is. Most algorithms require many calculations, and the sequence of steps is important. We need to pay extra attention to the process to handle the possible iterations and branches that exist during calculation. Column addition is a typical algorithm. For simple calculations, we can skip complex steps. For example, when we see 1 plus 1, many of us blurt out the answer 2. But when this becomes abstract numbers, like 23, 127, 386, plus 12, 983, 718, complex steps are required. Most people cannot immediately get the answer when they see such a large number, like 23, 127, 386. We need time for inference. Some people can immediately identify familiar plants with just a look. Like this is Aprinum aurum, while others may misidentify plants. This is Aprinum aurum, and that one too. When unfamiliar with the plants, we may need to infer based on the leaves. Computers are different from humans. They do not see the input and deliver the result. Any result is delivered after step-by-step calculations. The procedure is an algorithm. So what are algorithms? Algorithms are defined by limited steps or sequences that are executable on computers. They are commonly used for computing, data processing, and arithmetical reasoning. Algorithms have the following features: certainty. Each step is deterministic, ensuring unified understanding of an algorithm's description for programmers. Finiteness. The steps of an algorithm should be limited, and the execution can be determined. This avoids infinite loops, to ensure every algorithm has an end. Validity. Each step can be executed to deliver a clear result. Algorithms can have 0 or more inputs, which refer to relevant external information needed when executing an algorithm. Some algorithms don't need input, while others do. Therefore, inputs are not essential. Next, algorithms can have multiple outputs. They are focused on problem solving, and their outputs reflect the result. Algorithms without output are meaningless. They can survive without an input, but an output must be generated. True algorithms, calculations like we discussed earlier can be a simple addition like 254 plus 2448, or a move in the game Go, or the chance of rain tomorrow. Of course, correspondingly, algorithms vary a lot to fit the goal. So there is no set numbers or steps or storage space. The required calculation time and space are expressed as the complexity of the algorithm. Next, we'll look at simple algorithms.